Welcome everybody. Thank you for attending this session about the modeling and optimization. So I'm happy to share this session. Today we have 3 presentations during this session. So I will introduce the first speaker. So the first talk will be given by Eduardo Andres, who received his bachelor degree and Master of Science degree in aerospace engineering from the Technical University of Madrid in Spain in 2015 and 18 respectively. And he got another Master of Science in Flight Dynamics in Cranfield, UK in 2017. He's currently pursuing a PhD in aerospace engineering at University Carlos III of Madrid under the supervision of Manuel Solers. And his research interests include trajectory optimization, path planning under uncertainty, and flight control systems. So the title of the presentation is Parallels Random Rapid Trees, RRT, for flight planning considering ensemble forecasting of thunderstorm. So Eduardo, I give you the floor now.
Good evening, and thank you for being here. My name is Eduardo Andres, and I come from University Carlos III of Madrid in Spain. I'm here to present our work GPU Accelerated RT for flight planning considering ensemble forecasting of thunderstorm. I would like to thank the support from Daniel González Arribas, Manuel Sanjurjo Ribo, and Manuel Soler from my own university, as well as Mariam Kangarpour from the University of British Columbia in Vancouver. This presentation has been structured in 4 parts. First, an introduction and motivation of our work. Second, our algorithm for trajectory planning, the so-called scenario-based RT star, as well as the process of parallelization to decrease its computational time. Then some tests and results, how the algorithm behaves with and without this parallelization, and also how sensitive are the results if we repeat the simulation. Finally, we will present some conclusions and future tasks to improve the algorithm. So let's go with introduction and motivation. I usually like to begin with this slide. This was a 4-year-old Boeing 737 flying from Geneva to London Luton. It flew through a hailstorm and then like this. It was able to land safely with no casualties, but the aircraft couldn't fly again. And this is mainly the issue we need to address. Storms are dangerous, they are uncertain and dynamic phenomena that affect aircraft trajectories. They are an important source of delay and disruption for the ATM system and also compromise the safety of the aircraft and people on board. In the previous example, only the aircraft was affected, but it could have been worse. Our main objective would be to design trajectories that minimize cost and ensure safety in these stormy regions. For that purpose, we propose the scenario-based RT star. Now, when pilots plan a flight, they rely on weather charts that might become outdated once they are flying. They also depend on the weather radar, which has a limited range and is also focused on the front part of the aircraft. There are many ongoing efforts and projects to supply recent weather data to pilots and display it in complementary devices, such as an electronic flyback. The idea would be that satellite and radar observations, together with numerical weather prediction forecasts, are processed in a ground station and then sent to these devices, which are on board. Our idea is to go further. Based on this weather data, we would like to implement an algorithm that suggests different diversions, here in green, diversions to around storm cell, so that the pilots and air traffic controllers can decide which path is more convenient. So for that purpose, we need a methodology that is fast, and also we are making it compatible with ensemble-based weather product, which are now a trend in weather prediction. Now let's move to the second part of the presentation, our algorithm, the scenario-based RT star. RT stands for Rapidly Exploring Random Tree. This kind of algorithms have been used for path planning, mainly in robotics and autonomous vehicles. It is a sampling-based algorithm An iterative methodology to connect two states, as it can be observed in this picture. During each iteration, it takes a random sample from the free space and attempts to connect it to a tree. The idea is to connect the destination to the origin with a tree and its branches, which are called edges. If the total number of iterations is large, this algorithm is asymptotically optimal and minimizes a cost function, which for this problem would be flight distance. We have modified it to handle uncertain and dynamic obstacles described by a finite number of scenarios or ensemble members. Finally, with the use of GPUs and parallelization, it's able to provide solutions in seconds or a minute or two, depending on the iteration. In this figure on the right, you can observe an example of tree in green and how it grows, and also the solution of minimum distance in red. Now, the tree grows using three main functions. The first is called nearest neighbor. On the left, each new sample is connected to the nearest node in the tree. So let's take A30 and it's connected here to its nearest node in that iteration. But maybe the nearest node is not the optimal connection. So for that we have best parent function. In that case, A50, instead of being connected to the closest node, is connected to the one that involves less cost to the origin. Finally, we have rewire on the right. It's a function that is present during the whole simulation and it's restructuring the tree. This node, A30, at first was connected to one node, but now after 100 iteration, connection has changed. So these three functions are in charge of the growth and optimization of the tree. There is an additional function and really time consuming, and it's the one that determines if a connection is safe. It's present in all these three functions. Before we establish one connection, we need to check if it's safe. And how safety is ensured is explained in this slide. This is also what has been parallelized due to the computational time. The scenario-based RT star ensures that each trajectory formed by a sequence of tree branches or edges is safe with a safety margin which we denote by epsilon. For each trajectory, the sum of probabilities of each edge intersecting the obstacle set or the storm set must be below this safety margin, which is this equation in here. We assume that obstacles are uncertain and described by n sub sc possible scenarios. Each of these individual probabilities is calculated as the number of scenarios in which the edge is unsafe over the total number of scenarios. This number of scenarios in which the edge is unsafe is quite time consuming to obtain because it involves calculating if there is an intersection with each cell in each scenario. At first it was done sequentially, but the process was parallelized with GPUs, reducing substantially computational time, as I will show later. On the right, I include an example with a trajectory of two edges and a 10% safety margin. This first edge would be safe. There are no intersections, so the probability of being unsafe is 0. Then we have this edge here, which would be unsafe because the probability would be higher than epsilon. So this trajectory, if we follow it, we would be violating this equation. On the other hand, if the probability of this edge is lower or equal to epsilon, this whole trajectory would be safe and we could continue growing a tree from here. So let's continue with the case study and results. The idea is to find a trajectory between these two states, which are here and here on the map, minimizing flight distance and with a safety of 90% or an epsilon of 0.1. We have created this artificial ensemble of 20 members to represent uncertain storm cells. They are basically polygons. We are showing an static environment, but the algorithm is tested and works with moving obstacles as well. So the first relevant result is how parallelization affects performance. In this table we show the time that it takes to check if just one connection is safe, one edge, as a function of the number of scenarios of the members of the ensemble, which move from 5 to 50. Without GPU and parallelization, it's the order of seconds and increases as we increase the number of scenarios, almost linearly. However, with parallelization, the time reduces to milliseconds, and it doesn't depend almost on the number of scenarios. Time was reduced in 2 or 3 orders of magnitude, as you can see here. Now, if we consider a whole simulation for a predefined number of iterations, from 100 to 5000, without GPU, it takes hours or days, and we couldn't continue. It would take months to go through 200 or 500 iterations. However, with parallelization, it takes around seconds or minutes. 1000 would take around 2 minutes, and as I will show later, it would be enough for this case. In this slide, we show computational time for multiple simulations with respect to the number of iterations. They are represented in double logarithmic scale. The relation is quadratic, and doubling the iterations implies 4 times more computational time. So we should approach optimal solutions with the less iterations that we could to reduce this time. Now, going to results and trajectories. Instead of showing one solution, we would like to show multiple ones for different number of iterations, for 1 to 5000. The results, as you can see, are sensitive to the simulation and the number of iterations. Each time the tree grows, it does it in a different manner, and it might get trapped in different suboptimal solutions. As it is shown here, for 1 or 2000 iterations, there are 3 possible trajectories. But when we reach 5000, almost every simulation converges to the same trajectory. However, we consider that it's not necessary to go to 5000. In this figure, we represent the error in flight distance with respect to its minimum value as a function of the number of iterations. This minimum value was obtained running the simulation for 100,000 iterations. So here we consider 50 simulations and represent the 0, 10, 33, median, 66, 90, and 100 percentiles with different color bands. If we take a look at the median, after 500 iterations, the error was of 2.4%, and after 1000, only 1.1%. Moreover, after 1000 iterations, the maximum difference was of 3.2%, and 90% of the simulations were below 2%. Finally, some conclusions and future work. The parallelized scenario-based RRT star is able to produce safe solutions in a matter of seconds or minutes with a safety margin which is user-defined. It is also able to incorporate ensemble-based weather products to the planning, and additionally is able to provide different close to optimal solution, which can be a positive fact, as we will be able to give pilots and air traffic controller more than one safety path around storms. As future work, we would like to to extend to 3D problems and include more realistic weather data. Also, one thing that we are doing is improve convergence, as it's illustrated here on the right. The first picture shows the algorithm growing in each direction, minimizing paths towards every state, which is not really efficient. We are studying the use of informed trees, which are shown here on the right picture. They focus the search on the area of interest and make a better use of each iteration. So that means that the algorithm is able to converge earlier. So if instead of 1,000 iterations, we are able to approach the solution in 500 and requiring 4 times less computational time. So that would be 30 seconds instead of 2 minutes. Finally, we would like to explore how the number of obstacles or storm cells and the separation between them affect the performance and convergence of the algorithm. And that would be all. Thank you for your attention, and I will be pleased to answer any questions you may have.
Thank you, Eduardo, for this presentation. It was clear. Are there some questions? I see one question in. I will read the question. Perhaps it is easier. From Antonio Franco. Your work is interesting. How have you compared your algorithm with trajectory planning method based on visibility graph?
Thank you for your question. I did some research of that kind of graph, but I haven't compared it yet. It would be some interesting approach for the future, but at the moment we have not compared it yet. So thank you.
Are there just to see if there are some other? Right, not so good with this tool. Yes, it is the same. Are there some other questions? Feel free to ask question to Eduardo. So me, I have some questions for you.
Yeah.
Because I work with the same approach for emergency trajectory design. But so in 4D, when you take into account the time dimension in your algorithm,
yes,
you can avoid moving obstacle. But what about the speed of the aircraft?
Yes, that's true. That's something we need to address. For now, we are running it with constant airspeed, but
so in fact, when you propagate, when you follow the path given by the algorithm, you consider the aircraft is flying at the regular speed. But I think you can also, I don't know if it is relevant or not, but you can, after 1 hour, perhaps you can slow down the aircraft, perhaps to avoid a storm. I don't know if it is, it's this approach could increase a lot the complexity of the algorithm. I don't know. What is your point of view?
Yes,
having the speed as a decision variable in the optimization process.
Yes, that is something I have considered. Increase the number of states so the rapid response random tree takes samples of speed. So in that case, the algorithm might be able to change speed, but adding another state might cause the algorithm to be slower. So
yes, I think so. And this brings me to the next question, see if I can, yes. But I think it is possible, but I don't know if it is easy, but I think you can take into account the wind in your weather forecast. Also.
Wind. Yes. At the moment, we are just focusing on thunderstorms, but
because you can avoid a thunderstorm by the right on the left, I mentioned, but perhaps one option is more efficient from the fuel point of view. Sorry, because of the wind. I think it is not so difficult to include the wind in your algorithm. No.
Yes, that is something we are doing now, and We want to include fuel consumption and another uncertainty such as wind or temperature.
And I think, I suspect you program your algorithms with Python, something like that, no?
Yes, Python.
So I think if it could be another option to speed up the process is perhaps to use another programming language a little bit more efficient. And perhaps also, that is my last question.
Yeah.
Do you think it is possible to take into account the turning rate of the aircraft as a constraint when you propagate?
The turning rate. Well, this includes this simulation includes just a unicycle model, but we also included in some simulations Davin's curves, which model the radius in the turn. I don't know if.
No, it's just I like this work because, but it is not easy to do such a planning. And at the end, you get the geodesic trajectories, I think, yes. Okay, so if there are, I see another question in the assembly, sorry, from Antonio. So yes, I agree with Antonio. So Antonio mentioned that the non-holonomic constraints are quite difficult to include, isn't it?
Oof, yes.
Yes, I agree with him. So I fully agree with that. So
yeah.
Thank you very much. So
Thank you.
are there some other questions? No. So nice work from Antonio. You have a fun. So I would like to upload you, but it's not so easy with internet. So thank you, Eduardo, for this nice presentation. So I will shift to the next presenter. So next presenter is E-AMAN. I know her very well. She was my former PhD student. So she's E-AMAN Jeff. She's currently a fellow at SAB NTU Joint Lab at Singapore. And she's working with my friend Samir. Research includes implementation of new data-driven metrics for remote tower control center. A previous research addressed the air traffic management at the ATMRI, was the objective to reduce the terminal maneuvering area congestion. And she did a PhD in applied mathematics from our school, from IANAC school in Toulouse. So, E-AMAN, I think I can give you the floor. It's okay for you, E-AMAN?
Thank you, Daniel. Hello, everyone. Thank you for having me. So first, please let me share my screen. Okay. Okay, hello, everyone. So my talk today is about a speed control strategy for Extended-AMAN using holding detection and delay prediction model. So during this presentation, I will go through this plan. So first, I will introduce our problem. Then I will present our proposed approach, which includes two sections. The first one is a holding and delay prediction model. And the second one is a speed strategy to absorb approach phase delay. Then I will present some of our experimental results. And finally, I will conclude with some conclusions and perspectives. So I will move to the introduction. The growth in air traffic demands put significant pressure in busy airports to optimize their resources and to look for cost-efficient solutions, especially regarding the post-COVID pandemic. Currently, most of the airports are operating at their maximum throughput, especially at peak hours, which cause the increase of flight delays, particularly at the TMA airspace. These delays are expressed in terms of holding and route extension assigned to the flight by the controllers. These maneuvers cause side effects like TMA congestion, the increase in fuel consumption, and the environmental impacts. In order to manage this problem of holding at lower altitude, the Extended-AMAN was introduced. The Extended-AMAN is an upgrade of the current arrival manager system, which is a system established to provide the optimal arrival sequence. The main difference between AMAN and Extended-AMAN is that the AMAN system operates within 150 nautical miles from the touchdown. However, the Extended-AMAN extends the coverage horizon up to 500 nautical miles. The main concept of the Extended-AMAN is to slow down the aircraft speed in order to absorb the holding time at the cruise phase, which we can see it here in the figure. So the current situation is in the blue line, where the aircraft experience holding in the approach phase. However, the orange line with the Extended-AMAN concepts, the aircraft slow down in its speed at the cruise phase, so that the approach phase is clear of any extension and holdings. The Extended-AMAN is already implemented in several cities in the world, like Rome, Amsterdam, and London, and it demonstrates success in ensuring smooth and efficient TMA traffic. Also, validation trial prove reduction in aircraft fuel consumption by an average of 8% per flight, and in airborne waiting time up to 90%. Despite the increase, the benefits expected from the implementation of Extended-AMAN, an accurate prediction of the arrival flight time and delays remains very challenging, because the flight trajectory in the TMA presents a complex holdings and trajectory extension due to the vectoring by the controllers. Also, by extending the coverage radius up to 500 nautical miles, the uncertainties in estimating the arrival time rises. These inaccuracies in arrival time computation cause perturbation in flight landing sequence, which in turn cause the regeneration of delay in the TMA. These delays absorption mechanism will no longer be efficient because of the inaccuracy of the prediction. So that's why, sorry, excuse me. Oh, sorry. Yeah, sorry, excuse me. So in this work, we propose a methodological approach for transferring the flight delays and holdings from the approach phase to the cruise phase. Our proposed approach includes both data-driven and optimization techniques. We first propose a method to detect the holding pattern from historical trajectory data. Then we propose a prediction model to predict the holdings and delays at 200 nautical miles from the airports. After that, we propose an optimization model that takes the predicted delay as an input and provides the airline and the NSPs with adequate speed adjustment. So we can see here the graph of the, we can see here the concept diagram of our proposed approach. We have first the delay prediction model, then we adjust the aircraft speed at 200 nautical miles, which results in absorbing the delay at the cruise phase, and the approach phase is now clear of the holding and vectoring. So now I will start with our first section, which is holding and delay prediction framework. In this work, we use 1 month of arrival flights to Changi Airport. The data we have is a DSP data for all the arrival flights, and also we have flight plan data provided by a major airline in Southeast Asia. We also use the meteorological data, METAR. So the flow chart is presented in the figure here. We can see 3 main boxes. The first one is the data mining model, which includes the cleaning of the data, the holding detection model, and the feature engineering model. Then we have the second block, which is the holding time prediction model, which includes 2 models, the classification model and the regression model. And the third box is the delay prediction model, which also includes two submodels, the classification model and the delay prediction model. The prediction model is performed at 200 nautical miles from the airport. And let me here define the flight delay in our model. Actually, the flight delay at the approach phase is defined as the difference between actual duration in the approach phase, which is extracted from the ADS-B data, and the planned duration, which is extracted from the flight plan. So the duration in the approach phase is computed by the time from the initial approach phase to the touchdown. I will start here by presenting our algorithm for the holding detection. So you can see at the left-hand side an example of the flight holding pattern presented by the flight trajectory in the Dutch blue line. The solid blue line presents the segment of the flight path. So first, we use a Kalman filter to estimate the flight velocity component at each trajectory point. Then this velocity component is projected in the flight path, which results in the graph in the right-hand side, the variation of the speed component relative to the time. After that, the holding is detected if the velocity vector includes a sequence of negative values. Once we detect the holding, the time of holding is derived by computing the first turnaround time, which is given by TA, and the second turnaround time, which is given by TB. These two times, TA and TB, can be derived from the zero crossing in the projected speed profile. Then the holding time is equal to twice TB minus TA. So now I will move to the prediction model. The first section is the feature engineering. So here we consider all the features included in our model. The first one is the flight information, which includes the region, the departure airport, the weight category. Then we have the flight parameter at 200 nautical miles, which includes the latitude, longitude, heading, altitude, and speed, which includes also hour of the day and day of the week. We use also flight path, like airways, stars, and runway. We use the surrounding traffic, and also we use the weather from the METAR, and we translate this METAR to ETMAP weather index. We use as well airport performance metrics like arrival and departure runway capacity. So these features are included in the holding and delay prediction model. So here we can see the flow chart for our model. The first block is the holding prediction model, and the second one is the delay prediction model. The holding prediction model includes a sub-process, which is the classification model, which predicts whether the aircraft will go on holding or not. The result of this classification model is the probability of holding. This probability is an input for the holding time prediction model, which is a regression model and predicts the total holding time for the aircraft at the approach phase. The result of this first model is the predicted holding time, which is used as an input, as a feature for the delay prediction model. Now, the delay prediction model also includes two processes. The first one is the classification, whether the aircraft will be delayed more than 2 minutes or not. The result of the classification model is the predicted probability. This probability is included to the descent approach, the approach delay prediction model, which it's included like a feature in the model. And the delay prediction model is a regression model, which predicts the total delay of an aircraft in the approach phase when the aircraft is at 200 nautical miles. The result of this model is the predicted delay. Now, once we have the predicted delay for all the aircraft at 200 nautical miles, we move now to the speed strategy to absorb this predicted delay at the cruise phase. So the speed strategy to absorb approach phase delay aims at slowing down the aircraft speed in order to transfer delay from approach phase to the cruise phase. The prediction model was performed at 200 nautical miles. However, for the speed strategy, we investigate three radius, 200, 300, and 500 nautical miles, as presented in this figure. So we consider virtual concentric circle centered around Singapore Changi Airport, which we refer to as the range ring. Also here we consider two-speed reduction strategy. The first one less than 10%, and the second one a speed adjustment between 3 to 6%. So the concept diagram of our proposed approach is presented in the figure. So the blue line represents the original trajectory and the red line represents the resulting trajectory after speed control. Our objective is that the aircraft will adjust its speed in the intermediate waypoints and reach the initial approach fix with the original time plus the descent delay. Also, we want that the aircraft do not change the landing performance. So our constraint is that the aircraft will reach the initial approach fix with the same speed. To implement the speed adjustment and the speed change, we assume that the aircraft perform constant deceleration in each segment. Now, in order to compute the adequate speed change for each aircraft, we model the problem as an optimization problem. So here is our optimization problem formulation. Our input data for each flight is the actual trajectory points. Then we have the flight speed profile for each at each trajectory point, and we have the predicted delay, which is resulting from the delay prediction model. Our decision variable here is the assigned ground speed for each for flight F at each waypoint. This assigned speed can be expressed in terms of the speed rate of change. So our constraints we consider two speed adjustment maneuver. The first one is the rate of change less than 10%, and the second one, the rate of change between 3 and 6%. The objective function here, we consider three objectives. The first objective, we want that the aircraft absorb the predicted delay before reaching the initial approach fix. The second objective is to reduce the rate of change for all the aircraft. And the third objective is to reduce the number of regenerated conflict at node and link. So the objective function is to minimize the weighted sum of these three objectives. Now I will move to some experimental results. So here in this work, we consider the arrival flights to Changi Airport on the month of May 2019. We have a DSB data for all the arrival flights. We have flight plans provided by one airline. So here the initial number of flights is 13430. The number of flights after data cleaning is 9376. The number of flights with flight plan is 2091, and the number of flights with holding is 679. Now, the number of flights with flight plan and holding is 163. The results of our holding detection algorithm show that the algorithm is able to detect all the trajectory with holding. So here we can see at the left-hand side, 100 flight without holdings. At the right-hand side, we have 100 flight with holding. Now I will present the holding and delay prediction results. So for the prediction model, the data is split into 80% training and 20% test. The threefold cross-validation are performed to determine the optimal parameter for each prediction model. Also here, this figure presents the star routes for the arrival flights to Changi airports. In our model, the flight trajectory are categorized into 4 star groups. For each group have its own prediction model. So we can see that, for example, the star group 1 is for flights approaching Singapore from the north. Star group 2 is for flights approaching Singapore from the east. Star group 3 is flights arriving from the south, and star group 4 flights arriving from the west. So this is the holding prediction results. The classification accuracy is 92.9. And the holding time prediction is presented in this table. So we have the for each star group, the number of flights and the mean and standard deviation of the holding time. We have the results with the holding probability and the results without using the holding probability in red, and the results with when using the holding probability in green. So we can see that when using the holding probability, the root mean square error is reduced, is strongly reduced, and it is less than 1 minute. However, without the holding probability, the root mean square error is almost the standard, equal to the standard deviation. Now I will present the result for the delay prediction. So here we have the delay classification accuracy 69.5. Actually, even though the classification accuracy is not very high, we are more interested in the prediction accuracy of the regression model, as this classification model provides only an input for the delay prediction. Now, for the delay prediction results are presented in the table here. Here we have less number of flights because we only consider flights with flight plan, where we can compute the delay for those flights. So the results of the prediction without using the delay probability and predicted holding time is in red, and the results when using the delay probability and predicted holding time are in green. And we can see that the prediction performance improves across all the star groups when including the delay probability and the predicted holding time. Now I will move to the speed control strategy. So here we consider a scenario with 3 days of traffic. The number of flights is 762, and among these flights we have 80 flights with delay. The total amount of delay is around 8.5 hours. So here we consider two speed strategy. The first one is speed adjustment by less than 10%. And the second one is the speed adjustment between 3 to 6%. So the histogram here shows the absorbed and remaining delay within different range ring and different speed strategy. So we can see here, for example, at range ring 200 nautical miles, the amount of delay transferred to the cruise phase is around 20 to 18%. The delay transfer at the range ring 300 nautical miles, the delay transfer to the cruise phase is from 20 to 30%. And we have more interesting results from the range ring 500 nautical miles, where we are able to transfer from 40 to 70% of the delay. The delay statistics for different speed control strategy are presented in the table below. So we have first, the mean initial delay is around 6.4 minutes per flight. When applying the speed strategy, the mean absorbed delay can reach 4.3 minutes for the range ring 500 nautical miles, which is equivalent to a mean remaining delay 2 minutes per flight. These are the results for a scenario including 500 flights delayed by more than 2 minutes. The initial total delay is around 50 hours. And we apply here the speed strategy one. So the figure here shows the percentage of absorbed delay in each star group. We can see from this figure, at least, we have here at least 60% of delays are absorbed at the cruise phase when applying the speed strategy one with the range ring 500 nautical miles. So the 60% of delay, which is equal almost to 30 hours. For example, the star group 3, we have 85% of the delay are transferred to the cruise phase when we start applying the Extended-AMAN at the 500 nautical miles. Now I'll pass to the conclusions. So in this work, we propose a method to transfer flight delays from the approach phase to the cruise phase. So here we have three main contributions. The first one is a new holding detection algorithm to detect flight holdings and holding time from historical data. Then we propose a data-driven model that combines classification and regression model to predict the flight holding, the holding time, and the flight delay at 200 nautical miles from the airport. Then we propose a speed strategy to absorb the predicted delay at the cruise phase. The computational experiments are conducted using 1 month of air traffic arrival flights to Changi Airport. So the main important observation here is that predicting flight delays is strongly correlated with the prediction of holding pattern and duration. The second is that applying the speed control at 500 nautical miles contributes to transferring up to 85% of the delay to the cruise phase, which help to reduce the workload of the TMA controllers and also to reduce the fuel consumption caused by holding at lower altitude. In the future work, we propose to investigate the holding and delay prediction model at 300 and 500 nautical miles. We also propose to investigate a dynamic speed adjustment, which better manage the delay prediction error and uncertainties. Thank you for your attention.
Merci. Oh, sorry, I speak French. Thank you very much, Imen. And are there any questions on the attendees? I see one question for you from Extended-AMAN. I hope I pronounced correctly. I asked for a similar question in another section. Sorry, is the speed adjustment containing wind effect from common wind at the cruise level is positive or negative, and just throttle adjustment for speed adjustment, or what is the foresight for controller workload and the speed adjustment, and the uncertainty in terms of weather? So how would you manage the wind, roughly, if I can summarize?
Actually, in this model, we did not include the weather in the en route phase. So we only include metadata for the prediction model. But I think the question is for the en route, right, for the speed adjustment. For the speed adjustment here, we do not include the wind. But actually, based on some of the literature work, they mentioned that the speed adjustment up to 10% do not increase the controller's workload. But in our work, we haven't investigated the impact of wind in the cruise phase.
Are there any other questions? The attendees? I see some others, sorry. Thank you. So Logan Jones has a question for you, Imen. I think yes. I see you use an initial classification, holding, I mean, followed by a regression to determine how much holding delays. Did you use this approach as it provided better accuracy than using just a regression, or using multi-category classification, example, not hold, 5 minutes, 10 minutes, something discrete?
Yeah, actually here we use the classification model because it, and the predicted probability, because it improves the accuracy of the regression model. And in the results section, I present two results, one of without using the probability of holdings, and the second one when including the probability of holding. And the accuracy of the model improves a lot.
Thank you. Just go on with the questions from David Rodriguez Madridejo. I think, I'm sorry if I did not pronounce clearly. So the question from David is, when clearing a new speed, so you change the speed of your aircraft, is it likely that it will affect to another flight in the area of responsibility of the ATCO? So you can reduce and you can create conflicts, like you mentioned. So maybe potential conflict could arise, and so an increase in the workload. Why this taken into account? The negative impact of your decision, if I can say.
Yeah. Actually, the generated conflicts are included in the objective function of the optimization model. So when we run our optimization, we notice that there is no generated conflict. This is maybe because we are using a small set of flights, because we ran the model for 3 days of traffic. So for these flights, for this data set, we noticed that there is no generated conflicts, new conflicts.
Okay, thank you.
Actually, we included in the objective function.
Okay. So another question from Michael to Dresden. It shifts from one to another. Anyway, I will pick the one of Michael. Are there any specific constraints at Changi? Could you easily transfer the model to another airport? I mean,
okay, so here I can transferring the model to another airport.
Like London or like Paris?
I think here the only specificities we included is the information of the star trajectories, the behavior of these flight trajectories, but we did not consider something specific for the Changi airport for our experiments.
Okay. Sorry. Another question from Luis Meo, perhaps I pronounced not correctly. So he thanks you for your presentation. I think you know him. Since holding prediction seems reliable, have you explored predicting holdings after the cruise speed was adjusted? So you take your decision. So what's happened after?
Yeah, actually here we do not reduce the number of holdings, but we do reduce the delay. And the delay is computed based on the extension of the trajectory or the holding. So it can be holding, it can be only extension. So for example, as we see, the number of flights with holding was with only for the flight with flight plan was only 160 flights. So we consider both flights with extension and flights with holding, and we try to reduce this delay, the time of the delay. So I'm not sure how we can, I mean, because the amount of the delay was reduced, but if the remaining delay will be in terms of holding or extension, actually we are not sure of that, but we just reduce the delay, including the holding and the extension of the approach trajectory.
Are there any questions from the attendees? I have some for you, Iman. So perhaps I didn't catch something about your optimization techniques, but which kind of approach you use to optimize in the second phase of your work?
You mean the optimization algorithm? Here we simulated annealing.
Okay, yes, because it is quite an NP problem.
Yes.
I have just something, I was surprised about your last slide, but it is not because of you, because I think in Cerebro airspace, you have a lot of oceanic airspace, because having a holding in the en route space, I think in Europe, it is impossible, it's too big.
In this terminal airspace?
But you mentioned you expect to detect holding and 300 nautical miles away from the, perhaps I didn't catch the last sentence.
Yeah, actually, we want to, yeah, I see. So we want to predict when the aircraft at 300, we want to predict of whether this aircraft will perform a holding at the approach phase or.
Okay, because having a holding in our route airspace, it's too big, so I didn't catch that.
Yeah.
And the last thing, but perhaps it is just an extension for you and your advisors. I think it could be a little bit more, not challenging, but more benefit to predict and to act on the seconds by doing relative speed control instead of absolute speed control. You know what I mean?
Relative speed control.
Yes, instead of building the seconds or predicting the seconds as arrival, it is linked to what you do. But I think it is, you will gain more benefit on the action of the aircraft. I don't know, but that is just something it could be interesting to address. Instead of checking the delay for each aircraft, to think about the relative delay between aircraft, and in order to give a relative speed control instead of absolute speed control. Okay. Depending on the wind, for instance, or things like that. But just, I don't know, but it could be nice to address this tension. Are there any questions? I see one. No, it is a chat, so it's okay. Man, thank you for your nice presentation, and I propose to shift to the next one. So I upload, but it is, you understand. Huh?
Thank you so much.
Thank you. So the last presentation for this afternoon will be given by Emira. I want to be correct with Homira Kaledian. So sorry if you did not pronounce correctly your name. You are from Iran formerly. So you hold your master in signal processing from Iran University of Science and Technology. Sorry. No. She worked in an institute as a researcher at Sharif University of Technology in Iran too, from 2017-19. And in 2019, she started a PhD in the aerospace science and technology at the Technical University of Catalonia under the supervision of Xavier Prat and Dr. Jordi Villa-Valls. And she's working in aircraft trajectory estimation and prediction. So, and I want to be correct. Omira, sorry.
Omira, yes.
Omira, sorry. It's up to you.
Okay. I need to share my presentation.
Yes, you can share your presentation.
Okay. Hello, everyone. Good afternoon. And today I'll be talking about real-time identification of high-lift devices deployment in aircraft descent with the subtitle An Interacting Multiple Model Filtering Application Validated with Simulated Trajectory, which is a collaboration between me and Associate Professor Dr. Xavier Prats from Universitat Politècnica de Catalunya, UPC, and Associate Professor Dr. Jordi Villa-Valls from Isai Supairo, University of Toulouse in France, which both are my advisors as well. The main concepts in this presentation, I'll start with the introduction, then I'll give you a brief background in this topic, then I'll go for system model and filtering strategy, and then I'll show you the results and a little bit I'll discuss on them. And I'll be finishing the presentation with the conclusion and some idea about the future works. Well, having an accurate ground-based trajectory prediction is extremely important to design the next generation of air traffic services, since the new generation of air traffic management are based on trajectory-centric paradigm or trajectory-based operation. And to enhance the decision support tools for traffic synchronization and separation management, for instance, in arrival or departure managers, by having an accurate ground-based trajectory prediction, we can arrange arrival or departure more efficiently. And to enhance safety nets and collision avoidance tools such as medium-term conflict detections, either in an automated environment, on-ground, airborne, or in a distributed systems. And more importantly, to develop a real-time ground-based monitoring systems, it would be able to detect atypical trajectory or unstabilized approaches. Well, we say that an approach is stabilized if all the following criteria are met when the aircraft is at a given height above the runway threshold, which typically it's around 1,000 feet. When the aircraft is on the correct flight path and has a constant approach speed, is with the correct landing configuration, which could be flaps and slats, and has a stable descent rate within some margins, for example, not exceeding from 1,000 feet per minute, and has a stable descent flight path angle. Well, what's the objective of our paper? Here we are dealing with real-time identification of high-lift devices deployment based on surveillance input data, which it means that our measurements are from radar or ADS-B. And we expect that this estimation aims to enhance ground-based trajectory predictions and aiming at detecting atypical trajectories or preventing unstabilized approaches. Here in this figure, you see the flaps and slats of which are deployed on the wing of the aircraft. So what's the scope of this paper? Actually, we are working on the execution phase of the flight, and we are taking into account a model-based methodology to identify in real time the moment that flaps and slats are deployed on descending trajectories, since we are focusing on the aircraft descent. And we're going to detect the deployment moment of the first flap configuration, which we expect that our work would be capable of being implemented in real-time applications. So what's the high-lift devices? Actually, as all you know, the wing of the aircraft are equipped with high-lift devices to actually allow the aircraft to fly in a lower speed and consequently to reduce the landing and takeoff distances. So those devices are designed to be used in the takeoff and initial climb and final stage of the approach and landing. And commercial airlines, usually their aircrafts are equipped with flaps and slats. So in this work, for high-lift devices, we are considering flaps and slats as our high-lift devices, which have different positions or configurations. Depends on the circumstances of the flight, and also depends on the type of the aircraft. And those are progressively deployed during the approach and progressively retracted during the climb. Well, we have two main categories of these circumstances flight, for which could be clean configuration, which means all the flaps and slats are deployed, are retracted during the flight. So there is no flaps and slats deployed. Or depends, as we said, depends on the type of the aircraft. We have different positions. For instance, in Airbus A320, we have 5 different configuration settings, including Conf 1, Conf 1F, Conf 2, Conf 3, and full configuration setting. Well, each flap and slat configuration has a minimum and maximum speed. It means that the pilot needs to deploy or retract the flap and slats at a determined speed. And there is different drag coefficient parameters. It means since the flap increase the drag forces, so at each different position, we have a different drag coefficient parameters. Other things that could influence on deployment moment to detect the exact deployment moment are weather, especially strong wind and or gusting wind, and obstacles which are below the flight path, or how busy is the crew in performing other tasks. For example, communicating with air traffic controller or other things, since deploying or retracting the flap and slats are quite manually. Regarding the aircraft intents, what is aircraft intents? Actually, we consider a vertical domain. So in this vertical domain, we, at each time step, we have 2 intents to close the 2 degrees of freedom of aircraft dynamic. It means that the pilot needs 2 intents to steer the aircraft. And different combination of these intents are possible, which all the possible aircraft intents in this paper are summarized in this table. For instance, flying with fixed throttle and deceleration, or fixed throttle and constant calibrated airspeed. And here in this fig, I'm showing you the typical descent from cruise to the runway. And taking into account that we are flying in a cruise with constant altitude and constant speed. And each color in this typical descent shows the different, shows a typical different kind of aircraft intent, which is a combination of these 2 intents, and the vertical blue lines shows the configuration setting, the starting time of configuration setting, and the yellow point, actually the yellow point shows the first moment that the pilot decides to deploy the flap, which is conf 1. And we want to actually estimate this yellow point. Regarding the system model and filtering strategy, in general, the nonlinear discrete state space model are defined based on these 2 equations, which in these equations, F and H are process and measurement functions. And X is the state vector, and the initialization of the system are coming from the flight and weather data. And the measurement vector Y is the measurement vector, which are coming from ADSB and MOD-S. And the control vector, actually U in these equations is a control vector, which we have 2 parameters in this control vector, which are throttle and thrust and flight path angle, which since directly we don't have access to these thrust and flight path angle. So, and the aircraft is directed by the pilot or autopilot, since we define the pilot or autopilot input parameters vector in this P vector. And at each, as we said, since we consider point mass model assuming a continuous vertical equilibrium, so at each time step we consider 2 of these parameters to actually obtain the this control vector. And regarding the methodology, actually, we know that Kalman filter in a single linear dynamic state space model is optimal. And if the system is nonlinear, I mean in single nonlinear dynamic state space models, extended version of Kalman filter or EKF is the solution, is the optimal solution. But since in our work we are facing with different aircraft intent at the same time, so we are using interacting multiple model. And since the system is nonlinear, so we are using the extended Kalman filter interacting multiple model. So what is interacting multiple model? What is this IMM? Actually, the IMM is divided into 3 steps. At the first step, actually, what's the input? The input are estimated expected value and covariance of state vectors for all different modes that we could have, and their own actually their own probabilities. So in the first box, by combination, by mixing these expected values and covariance matrices according to their probabilities, we prepare the inputs for all EKF filters inside the second box. So inside the second box, what's the output of the second box? The output of the second box would be the updated version of expected values and covariance matrices of each state vector state vectors for each modes and their own probabilities. And at the end, by combining all these outputs from the second box, we will have the updated version of expected value and covariance matrix for the E-AMAN. And here in this paper, we are using this output as a solution in terms of identification of deployment moment. Another thing is moving average technique. Actually, moving average algorithm is a kind of technique to smoothing out the probability. Imagine that we have this response for the probability, and at this time, if we say that the maximum probability would be the moment that we would represent the mode that has the maximum probability at that time step. So if we say that at this time step we have the maximum probability, and we reported this time step as the moment that the pilot deployed the flap configuration, then it would be wrong. So we are using the window with 5 samples to smooth these probability and consequently to reduce the false alarms. So and that's obvious by having this delay in our work, we are reducing the performance, but this is a trade of increasing the robustness and reducing the performance. And in this slide, I'm showing you the whole story of our paper with this figure. Well, first, the trajectory simulator as a validation trajectory and input data are performing. Then by passing through Monte Carlo simulator and adding white Gaussian noise, we create the ADSB Mod S emulator. And then by applying the E-AMAN algorithm and moving average over probabilities, we will find the maximum probability and consequently the estimated deployment moment of flap configuration. And then we have estimated moment, and we want to compare this estimated moment with the real moment that the pilot deployed the flaps, and then we will see the performance of the algorithm. Well, regarding the results, the trajectory simulator generates flight data based on ADSB and Mod S receivers. And since we said that we are in a vertical domain, so we created 8 different validation trajectories, actually vertical profiles. And here you see the first validation trajectory just as an example. In this fig, you see the validation trajectory. The blue one shows the altitude, the orange one is calibrated airspeed, and the red one is true airspeed. And this trajectory, this validation trajectory contains 8 different phases. And at each phase, we define the aircraft intent by combining the possible intents. And we have the end conditions. In this figure, the vertical pink lines show the first time of each phase, the starting time of each phase. And then we have the configuration setting, what's the type of configuration and what is the landing gear position. And the yellow line in the vertical yellow line and the horizontal yellow line shows the exact moment that the pilot decides to deploy the flap for the first time. So we are going to estimate this vertical time, this actual transition time from clean configuration to conf1. And here you see the results. Actually, on top of the figure, we have the real model. each color shows the different aircraft intents. For example, this dark blue shows flying with fixed throttle and acceleration with clean configuration. And in this real mode, I'm showing you only two modes at the vicinity of the true time that deployment, we have the deployment moment. So this vertical line is the true deployment moment. And in the below, we have the estimated, we have the output of the E-AMAN and moving average as our output, and the shows the estimated model probability. And what does it mean? Imagine that here in this time step, it means that the probability of this model flying with fixed throttle and acceleration in clean configuration is around 40%. And flying with this aircraft intent, vertical speed and acceleration and clean configuration is around 20%, and so on. And this vertical dashed line actually is our output, the estimated moment, the estimated moment of flap deployment. And here we see that there is a little bit delay between the true one and the estimated one. There is two reasons for this delay. The first one, as we said in the previous slides, we are adding moving average algorithm, which by adding this algorithm, we will have more, we reduce false alarms, and also we reduce a little bit the performance of the model. But another reason is that since the E-AMAN needs a little bit time to adapt itself with switching from one aircraft intent to another one. So that's the reason for the delay. And here you see all the, since I said we had 8 different validation trajectories, here you see the results for all the validation trajectories. And in this figure, I'm showing you the performance error in unit seconds for seconds unit for all the validation trajectories. And as you see, the maximum error is less than 15 seconds, and that red points shows actually the outliers for each validation trajectory. So I'm going to summarize the presentation. So in this presentation, we use the E-AMAN filter to have a real-time identification of flap deployment moment in aircraft descent using surveillance input data. That aircraft following different aircraft intent, each one related to a specific dynamic model, and multiple model filters was able to identify the difference between clean and, I could say, non-clean, or other positions of the first time that we that the pilot deployed the configuration setting. And the model probabilities were used to determine the flap deployment moment, flap or slats deployment moment. And we applied moving average to avoid false alarms of the proposed method. And the preliminary results in this article show a good performance of the E-AMAN based flaps and slats deployment identification. Okay, regarding the future works. Actually, we are planning to use historical data gathered from ADSP receivers to assess the method proposed in this paper, and the identification between other configuration settings, since in this paper we were focusing on the first flap configuration, but in the future we're going to find other kind of configuration like conf2 full configuration, and also landing gear position. And the impact of identification of real-time flap deployment on ground tools will be analyzed, and improving the moving average. We're going to improve the moving average algorithm, and atypical trajectories will be taken into account to validate the proposed method. And at the end, other types of aircraft will be considered. And thank you very much for your attention.
Thank you very much. Thank you for the presentation. This reminds me some good souvenir when I did the radar tracking. So, are there some questions from the attendees?
Yes.
Just have a look, because we feel free. Perhaps people will have some other question after mine, but so if I well understand you, so for in the E-AMAN filter, you have a different linear model usually, or when I work on that, it was linear, but you consider one model for each configuration option?
One model? No, actually, we consider different models with different configurations.
Yes, but for one option of the E-AMAN filter, it is one possible configuration, something like that, or not?
One possible configuration. Excuse me, would you please a little bit?
Sorry, but I want to say, in the E-AMAN, you have you control and you estimate several models in parallel, and you do the fusion with probability fusion.
Yes.
And in your case, what are the input? What are the model? Are there regular Kalman, extended Kalman? I don't know.
Inside the E-AMAN, you mean?
Right.
Yes. Inside the E-AMAN, since we have non-linear system, so we are using the extended version of Kalman filter, so EKF.
EKF in each case, okay. My second question.
Yes.
So for controller, but not only for the controller, when you, I know you know like me that E-AMAN filter is able to do some prediction, but it is a short prediction. And do you think we could extend this approach to predict in a bigger time horizon? In the next 15 minutes, is it possible to predict what will happen for the configuration of this aircraft? It is quite ambitious, but I don't know if this is able to do that.
Well, yes, actually, we are focusing on real-time, actually, a real-time estimation. But if you mean for prediction,
because in the Kalman and the E-AMAN, you have a prediction phase.
You can use them for the prediction, but I'm thinking about 20 minutes ahead. And yeah, well,
not so bad.
Yeah.
I see one question. I will have another one later, but just from the attendee, from Ramon Dalmo. Hello, Ramon. So your model needs the probability from jumping, transitioning from one mode to another as input. Which are the probabilities that you assume? Do you think this matrix could be based on real trajectories using some kind of data mining?
Well, actually, I think he's asking about the probability matrix, the transition probability matrix, which here we are using a fixed stable for the standard E-AMAN, which we say that if we want to jump from the current mode, again jumping for again coming back for the current mode is around 98%, and for other modes, if you want to jump from one mode to different modes, it's less than 2%. But well, yes, I'm thinking of improving this transition probability matrix. But regarding some kind of data mining, real trajectories, I need to think of that.
So, and this would be, are there some other question? Thank you, Ramon. So I have one last question, because the good point of the IMM or Kalman filtering is to propagate not only the state, but the covariance. And this reminds me some previous work which has been done, sorry, with data mining with, for instance, neural networks and like at UDL for some other place. But I think in this case, when in your approach, you for future work, but you could perhaps see and have a look on the Bayesian neural networks, which are able to propagate a state and learn a state, and to propagate also the estimates, the covariance metrics. I see another one.
Yeah, that's
Jordi.
my advisor, Jordi.
So I don't know if the attendees can read, so I read for you, because so Jordi answered to Ramon, and he said the answer is yes, Ramon. If you have a large data set, you can estimate such a probability with data mining and or other machine learning based solution. So, and for this, I don't know, perhaps it will not work, but using Bayesian neural networks could be a kind of just an assumption to see, to compare what is the difference and the in terms of performance and things like that.
Yeah, you mean using Bayesian methods?
It is the special networks which propagate not only the state, but also like the Kalman filtering is. In fact, Bayesian network is like having, if I can compare, instead of having a neural, it is a kind of small Kalman filtering instead of having a neuron. So it can propagate the state like a regular neural network, but also the covariance of the state, the confidence. So it could be something which could be applied for these things. I don't know, but this remind me.
Yeah, thanks for the comments. Yeah.
And are there some other questions? If not, I'm going to close this session. So I want first to thank the three presenters and the attendees to attend these sessions in the degraded mode. I'm sorry, like you, and so for that. And you have just mentioned to me, they mentioned to me they want to show you a small video. Is it correct, Michael? Teaser video.
Okay, thanks.
Beacon's general goal is to explore the role of AU's complex behavior, such as bounded rationality, in the design of new management procedures. In Beacon, we want to define models to capture the AU's decision process, exploiting the behavioral economics theory, with the aim of expanding the ATFM slots exchange concept, and in particular, improving the current user-driven prioritization process capabilities via the design of new market mechanisms. Based on the available data, we want firstly to create a strategic model with long-term planning capabilities for the agents, and then a tactical model to capture network effects and compute various key performance indicators and metrics to assess the impact these models have on the AUs and the entire ATM network.
Is advertisement? Yes, sorry. So it was just advertisement. So thank you again, and I hope we will see each other in 3D next year. Okay, bye-bye. Bye-bye.
Thanks, it was nice. Bye.
Bye-bye.
Thank you. Bye-bye.